Hello there. In this lesson, we're going to learn about some strategies to expand your ability to make Lewis structures of different types of molecules. Hopefully already you have some idea how to make single, double, triple bonds and how to show lone pairs, but we'll go over all of that as well. So first of all, recall that a covalent bond is a shared pair of electrons. So there's two electrons in there that are being shared between two atoms, and that holds them together. We're going to use Lewis structures or Lewis symbols to represent these molecules. And so typical way when you're learning would be to put the valence electrons of an element down, like for oxygen and water, and then bond the hydrogen to it. And you can use the two dots and circle to show a covalent bond. Now that gets a little tedious after a while, so you can graduate to some other representations. I tend to use sticks to represent the bonds, so you're welcome to do that. Some textbooks in different places show the electrons just on either side. And it's assumed that if the two electrons are between two atoms, that represents a bond. But I find that a little tricky because, especially when you're going to add more than one bond, it gets a little crowded. Anyways, so that's the format I'll be using, but you might see some others out there. Now, hopefully you remember how to bond molecules together from previous grades, but just as a reminder, a refresher, what we're going to do is we're going to start with the least electronegative element, so the element that's furthest from fluorine. We're going to put that one in the middle. It turns out for this one it's phosphorus, and you put your Lewis dots on the outside, and then you add the oxygen because it's the second least. And we'll put them around the side, and you can make a bond there and a bond here, and the fluorine can go over here. And you want each of these elements to end up with 8 valence electrons, as that is generally the most stable that molecules can be. And then if you can do that more quickly, you'll end up just doing a little quicker representation using the sticks. But make sure you include those lone pairs as well, because it's going to be important later on. You can also have different combinations. Carbon, of course, has 4 valence electrons. We're going to do the same thing with our oxygen. It has 2 free for bonding, and you could make a double bond there and leave space for the hydrogens. Hydrogens are special because they are fine with only having 2 valence electrons once they're bonded. So there you go. That's the typical grade 9 and 10 bonding. Now, when you compare the features of these bonds, you start to see some interesting patterns. And also, we're going to introduce our newest exception to the rule using resonance here. So first of all, single bonds, like we have here in this ethane, have a bond length of about 150 picometers. Now, picometer is like 1/1000th of a meter, so really, really tiny. So this measurement we aren't going to use too often, but just as a relative measure so you can compare, right? So you can see a single bond there with its bond length of 153 picometers and 345 kilojoules for every mole, which is a quantity of particles. So if we do a double bond like we have in ethene, you can see that because of those 2 pairs of electrons holding those carbons together, that the bond length is a little shorter and it requires more energy to break it. And so the pattern continues here. We got a triple bond between the carbons in ethine, and you see again that the bond length has gotten shorter again, and it's harder again to break. More energy needed to break that bond, so a higher bond strength. Now finally we get to these strange molecules that are called resonance. And so benzene is a classic one. It's got 6 carbons in a ring. Now when you do 6 carbons in a ring, what you see is that if there's only 6 hydrogens, that all these carbons are going to end up with not enough bonds. So that means we need some double bonds in here. And we have a choice. We could put the double bond here, and then skip that one and put it here, and then skip that one and put it here. Or we could have done the opposite, right, where we put the carbons on the second one around. Now this is different than just rotating the molecule. This is actually bonding those same carbons in a different way. And so what they find is when there's more than one possible way to draw it out, that actually the bond length won't be single, double, but they'll all be the same bond length at somewhere in between. So that means that these carbons are not sharing this double bond exclusively between the carbons indicated. So if we number them here, we got 1, 2, 3, 4, right, 5, 6. The double bond between carbons 1 and 2 here is not shorter than this single bond between carbon 1 and 2 and the other one. If you look at this structure using the technology that they have, you find that the bond length is sort of in between a single and a double bond length, which means that those double bond electrons are actually being shared equally amongst all of the carbons there. And what you have is a resonating structure. You can kind of think of it as flipping back and forth between these two and not really being either of them. So resonance structures are kind of special in that they're going to be sharing the extra bonds between multiple locations, which is kind of cool. So our next type of bonding that we're going to look at is coordinate covalent bonds. So this is going to add to your repertoire of ways in which you can bond atoms together. So a coordinate covalent bond is exactly the same as a single bond with one important difference. The difference is the way you've been making single bonds so far is you would take a single electron from one atom and you take a single electron from another atom, and those two are shared between the two. This one is 2 electrons being shared between the two, but one comes from a completely full orbital and the other from an empty. So instead of 1 and 1 making 2, it's 2 and 0 making 2. So let me show you an example here with ozone. So ozone is O3, and it has an oxygen, and you do your thing, and you're like 1, 2, 3, 4, 5, 6. That's great. I'm going to take another oxygen. I put it over here. 1, 2, 3, 4, 5, 6. That's great. I'm going to make this bond here. Awesome. I'm going to make this bond here. Awesome. And now I have a third oxygen. Now, where am I going to put that third oxygen? Well, that's where coordinate bonds can come in handy. So instead of drawing your electrons 1, 2, 3, 4, you're going to put the 4, 5, 6 over here, and you're going to leave an empty orbital. So empty orbital. And over here, we have a full orbital. And so what you can do is make a single bond between those two with 2 electrons from the other oxygen. So you end up with O and a single bond to an O and then a double bond to the other O. Now, did I have to put the single bond on the left and the double bond on the right? Well, no, I could have easily drawn it the other way around, which means that this is another example of resonance, because I could also draw this like so, right? With this double bond on that side and the single bond on the other side. So because there's more than one way to represent it, this is a resonance structure with more than one possibility. Alrighty, so let's try a few more here. We've got sulfur trioxide. So we'll put a sulfur in the middle here, and sulfur has 6, so 5, 6, and then we'll put an oxygen over here. 1, 2, 3, 4, 5, 6, and we can do yay, double bond, and then we're like, meh, now what? Well, we can do our same trick with the oxygen. Now, crowding the oxygen's electrons over to one side, that's called spin pairing. It leaves that empty orbital for coordinate bonds, and you can just represent that with an arrow if you want, first time you do it. And then, of course, when you get faster at it, you can just supplement that with a single bond. So you put sulfur, and you get single bond to one, single bond to another, and a double bond to this oxygen. So, again, When you look at this, you can say, well, did I have to put that double bond between that particular oxygen, or could I have used the other ones? And of course, you could have used the other ones, which means, again, we have resonance here. So I can put the sulfur with the double bond here, and ding, right? Or I can put the sulfur with the double bond on this side, and then ding and ding. And so what you're going to end up with is all these possibilities of resonance between the different ones, and you wouldn't have a short double bond and two longer single bonds. What you'd have is three equal bonds where that double bond electron is shared equally amongst all those possibilities. Now carbonate is an ion, and so for ions you have two extra electrons in this case to include in our structure. So we'll put carbon down, 1, 2, 3, 4, common strategy, we put the two extra electrons in the middle, and now carbon looks just like sulfur, and you can bond it the same way, right? You can make a bond here, another bond here, and then another oxygen up here, crowd them around, make our single coordinate bond in here, right? 1, 2, 3, 4, 5, 6. And of course, we can make resonance structures for the carbonate ion as well. Now, it's a good idea to put square brackets around this whole thing and show the charge just to represent or to show that there's two extra electrons in there to help make this bond work out. And of course, you could do all the different possibilities if you wanted to show the resonance structures for carbonate. Like so. There you go. -2 for all of these. And it'll resonate between all those structures. Great. Next. So our next tool for your molecule toolkit are exceptions to the octet rule. So most atoms end up with 8 electrons in their outer shell once bonded, but there are some that don't follow that pattern. You might notice in your chemistry classes thus far that we've avoided beryllium and boron, and that's because they don't always follow the rules, or often follow the rules. So beryllium is stable enough with 4 electrons in a molecule like BeCl2 so that it can be okay just existing that way and not have to resort to any other bonding strategies in order to be a stable molecule. Same with boron here. Boron can make 3 bonds with 3 chlorines and be perfectly happy that way, having less than 8 in its outer shell. So beryllium and boron are some common exceptions that have fewer than 8 in their valence shell, even when bonded. And there are some of these other ones, molecules that are called radicals. And an example would be NO2. So if you tried to bond NO2, what happens is you end up with a double bond to one oxygen from the electrons that you have free for bonding. And then you can do a coordinate bond with the other oxygen, right? You can do this thing. But you end up with a single electron left. And somehow that is also stable enough to exist. It floats around in our atmosphere. And so this is called a radical. It's when there's unpaired electrons. They don't happen too often, but there's lots of examples when they do. So there you go. Sometimes you'll have less than the full complete octet. Now the much more common occurrence is for the octet to be expanded. And so we can use these molecules here, PCl3 and PCl5, as examples. So doing PCl3, if you have your outer shell of electrons being phosphorus, you would say 1, 2, 3, 4, 5. And notice that there are 3 single electrons here that are available for bonding. Right? So that's great for PCl3, no problem. You put your chlorines on there and bond them, and you put another chlorine down here and bond it, and then another chlorine over here and bond it. Great, nice and stable, gets 3 more electrons. Let's use a different color here, 1, 2, 3 from the chlorines, and it's all good. However, we have this other molecule here that occurs too under certain conditions, PCl5. Now, we have the same 5 electrons. Now, how are we going to make 5 bonds there? How are we going to have 5 single electrons that are going to be able to make bonds with the chlorine? Well, what happens is a little trick called electron promotion. So one of these s electrons that was down here at the lower valence shell can be bumped up into this empty 3D subshell that doesn't have any electrons in it. So when you do that, you end up with 1, 2, 3, 4, 5 orbitals that are half filled, and that allows you to make all those extra bonds. And so you can do a chlorine on each one of them because they're now all each in a separate orbital, and you can bond them independently. I don't want to forget my extra valence electrons for chlorine here. Maybe I should have chosen hydrogen, it would have been easier. Anyways, there you go, all filled up. And down below, you would have an extra electron in each one of these orbitals to fill it up. And so apparently some molecules are more stable doing this. It isn't super common, that's why you don't do it in the lower grades, but it does happen, and so that's why we're doing it now so that you can see some of these neat exceptions. So let's try it with sulfur. Oh, still green. There you go. Sulfur. Sulfur has a D subshell as well because its valence shell is in the third shell. And so normally you'd have 1, 2, 3, 4, 5, 6 electrons, and you'd be able to make 2 bonds. However, we have 4 fluorines here, so how are we going to accommodate those 4 fluorines? Well, what we can do is we can erase this guy and then bump it up into this empty D subshell, and now we have 4 spots. And so sulfur can have 1 lone pair, which is this guy, and then bond to fluorine at 4 other spots. Something like that. The same thing over here. What we can do is take both of those electrons that were paired up originally and bump them up so that you end up with 1, 2, 3, 4, 5, and 6. And so now you can make 6 bonds with sulfur and end up with sulfur hexafluoride, right? So you have a fluorine here, and a fluorine here, fluorine here, fluorine here, fluorine here, fluorine here. And of course, oh my goodness, all these dots I have to put around here. Ding, 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 ding. And you can see that everybody's happy here, even though sulfur has gone beyond the 8 valence electrons, right? And you can plug in the fluorine ones down here if you want to complete the picture. And there you go. You have 6 bonds on the one and 4 bonds on the other. So I've introduced you to quite a few new tools for bonding molecules that you haven't used before, and it might be a little overwhelming for some of you. So I'm going to show you this electron counting method, which some students really like. And the great thing about it is it takes care of a lot of those different types of bonding that we've looked at. And so you don't have to consider them separately because the electron counting method can kind of do it for you. So let's try our first one here. We have iodine and 3 chlorines bonded together. Our first step is going to be to count up all the valence electrons. So we have iodine with 7, we have 3 chlorines also with 7, so that makes 28 valence electrons. We'll start by putting the iodine in the middle, and we're going to single bond everything else to it. So we got the 3 chlorines, they're all going to get a bond, and that's going to use up 6 of our electrons, so now we're down to 22. Then we're going to complete the octet for all of the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And so that means we're going to use up 18 more electrons there, and that leaves us with 4. The last set of electrons, we're going to put those in the middle. 1, 2, 3, 4. And so what you have here is iodine bonded to 3 chlorines, and you can see it's one of those ones that has done the valence shell expansion because the iodine ends up with 2, 4, 6, 8, 10 electrons in the center. But you didn't have to come up with it. The electron counting method did it for you. Now, this other example here uses sulfur and 3 oxygens. Sulfur has 6 and so does oxygen, so that makes 24 electrons. So we'll put the sulfur down here and we'll bond the 3 oxygens this time. And we will fill those up. So that uses up 6 again. It takes us down to 18. And then we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Great, uses up the rest of the electrons. We're down to 0. However, our central atom here is sulfur. It's not a beryllium or a boron, and it's not going to be happy without a full valence shell. So to take care of that, what you're going to do is you're going to share some of the electrons from at least one of those others that are out there, a lone pair that's out there. So we're going to change this. We'll erase this guy here, and we'll change those electrons to a bond, and we're done our job. Now, since I had a choice of electrons to use there, I could have used from any of those oxygens. That means this is going to be a resonance structure where you could show the different possibilities. All right, there you go. Hope that helps, and we'll see you soon.